Okay, just a couple more problems out of section R6 to wrap up R6. I did not have a chance to really get to these during class, and so I'm going to demonstrate these. If we were asked to factor this polynomial here, one way to do this problem is the hard way, and the hard way would be to multiply this all out and distribute the 2 inside the parentheses, and then gather together like terms and try to factor it from there. But there's a much easier way, and the easier way is utilizing something that's used often in higher level math, especially calculus. It's called a U substitution. U substitutions enable us to take a complicated situation and trivialize it. U substitutions help us see the forest for the trees. So a U substitution would be the way to go here in order to factor this polynomial. We can see that x squared minus 5 is a common factor between the first and the second term. Being the case, I would let a variable u be equal to x squared minus 5. And therefore, if u is equal to x squared minus 5, then u squared is going to be equal to x squared minus 5 quantity squared. So that being the case, I can take my polynomial up here and I can do my u substitution now. I can let u squared take the place of x squared minus 5 squared. And in place of u squared minus 5, x squared minus 5 rather, I'm going to replace it with u. So being able to being asked to factor this polynomial is really like being asked to factor this polynomial in the variable u, where u has been assigned this quantity here. Now it's easier to see what we need to do here. This, as it turns out, is a easy type of trinomial to factor, one with a leading coefficient of 1. To factor this type of trinomial, I need 2 factors of negative 24 that sum up or add up to give me a positive 2. And those factors, after some thought, would be 6 and negative 4. Therefore, this trinomial factors immediately into x plus 6 times x minus 4. U plus 6 times u minus 4. But we were originally asked to factor a polynomial in a variable x, not u. So it's very important now to back substitute what we let u be equal to. So back in for u, we have to substitute x squared minus 5. So therefore, x squared minus 5 has to be back substituted in place of u here and here. And therefore, we simplify this by combining our like constant terms here. We have x squared plus 1 times x squared minus 9. Upon further inspection, we realize that this needs to be further factored down, being the difference between perfect squares. And so, continuing our factoring, x squared plus 1 is the sum of squares, which cannot be factored. But this can be factored into x minus 3 times x plus 3. And we are done. We have completely factored this polynomial utilizing what's called a U substitution. So U substitution, again, its intention is to take a very complicated situation and trivialize it into something that is more easy to understand. And but in the end, you got to remember to always back substitute what you let U be equal to. And so this would be the complete factorization of this polynomial right here. All right, radicals. Radicals are like roots, square roots, cubed roots, fourth roots, etc., etc. So we're going to look at some radical operations here. All right, the first thing we're going to do here is take 3 times the square root of 5, and we're going to try to multiply this by the quantity 2 square root of 5 plus 4 square root of 2 plus 1. To do that, I'm going to utilize the distributive property. So the distributive property is going to enable me to take this and multiply it into each of these 3 terms here. So I'm going to have 3 square root of 5. It's going to be multiplied by 2 square root of 5. Plus 3 square root of 5 is going to get multiplied by 4 square root of 2 plus 3 square root of 5 is going to get multiplied over here by 1. Now, when we multiply radicals together, they must be of the same index. In other words, if this is a square root, this has to be a square root if we are to multiply them together. The quantities underneath the roots do not have to be the same when you multiply radicals together, because in general, if you have a times the nth root of b being multiplied by c times the nth root of d, we are justified in multiplying the quantities outside together. So a can get multiplied by c times the nth root of the quantities underneath the roots can get multiplied together, b times d. This in general is showing us how we multiply radicals together. So 3 square root of 5 times 2 square root of 5, 3 times 2 will net us 6. And the square root of 5 times the square root of 5 is the square root of 5 times 5, or the square root of 25. 3 square root of 5 multiplied by 4 square root of 2. 3 gets multiplied by 4 to give us 12. And the square root of 5 times the square root of 2 is going to be the square root of 5 times 2, or the square root of 10. Now, whenever we're working with square roots, we never want to leave a perfect square underneath the square root. It's not considered to be simplified. 25 is the perfect square of 5. Therefore, 6 times the square root of 25 would simplify to 6 times 5. 10 is not a perfect square, and 10 cannot be factored into anything that is a perfect square. So the square root of 10 cannot be further simplified. Therefore, we just leave it as 12 times the square root of 10. 6 times 5 is 30. So we have 30 plus 12 square root of 10. And this would be your final answer here. We cannot add the 30 and the 12 together because these are not like radicals. This has a square root of 10 attached to it. This one does not. So we'd have to leave our result as is. All right, let's try to simplify this next radical expression here. If I have 4 times the square root of t plus 10, and I want to multiply that by 3 square root of t minus 8. Well, we can borrow our FOIL algorithm that we use to multiply polynomials together to take care of this. This 4 square root of t can get multiplied by 3 square root of t. Plus, we multiply the outer terms together. 4 square root of t gets multiplied by negative 8. Plus, then we multiply our inner terms together. 10 times 3 times the square root of t. Plus, and then we multiply our last terms together. 10 gets multiplied by negative 8. Four square root of t multiplied by 3 square root of t. We multiply the 4 and the 3 together to give us 12. And the square root of t multiplied by the square root of t is the square root of t times t, which is the square root of t squared. 4 square root of t multiplied by negative 8. 4 times a negative 8 will net us a minus 32. And then we have the square root of t. 10 multiplied by 3 square root of 2, 10 times 3. You cannot multiply 10 by 2 because 2 is underneath the square root and 10 is not. You can multiply the 10 and the 3 together. 10 times 3 is 30 times the square root of 2. Finally, 10 times a negative 8 is minus 80. Let me double check everything here. I'm sorry, 10 times 3 square root of t should be 30 square root of t. This should not be 2, but t. My bad. This should be t here. That's t. All right, now 12 times the square root of t squared. The square root of t squared is just t, because when you take the square root of a perfect square, both the square root and the square disappear. This just simplifies to 12t. These are called like radicals. They can be combined. In general, how we combine like radicals is if I have A times the nth root of B plus C times the nth root of B. These are called like radicals. So to combine like radicals, I combine the quantities that are outside of them. So this will be equal to A plus C times, and the like radical part just floats along. Now, to be like radicals, both the quantity underneath the root have to be the same and the indices of the radical have to be the same. These are like radicals because they're both square roots of t terms. And so negative 32 of these square roots of t added to 30 of these square roots of t give us negative 2 of these square roots of t. And finally, at the end, we got minus 80. And this would be your result here, as we can do nothing else to simplify this any further. That would be your result. Here we're going to try to multiply two radical expressions together. 3 square root of 7 minus square root of 5 times 3 square root of 7 plus square root of 5. Well, ladies and gentlemen, these are called conjugates of each other because they only differ by the sign that's in between the terms. And multiplying conjugates together is pretty simple if you can remember an important pattern. Recall that we shown ourselves that A plus B in general times A minus B, when you multiply conjugates together, you always get the difference between the squares of the terms. So to multiply these conjugates together, you could FOIL this out, multiplying your first terms, your outer terms, your inner terms, your last terms, but there's a simpler way. Since these are conjugates of each other, we don't have to do that. All we have to do is just square our first term, square our last term, and place a minus sign in between them. Now, 3 square root of 7 squared is going to be 3 squared times the square root of 7 squared. The square of the square root of 5 is going to be the square root of 5 times the square root of 5, which is the square root of 25. 3 squared is 9, and when you square a square root of 7, you just get 7, because the square root of 7 squared is the square root of 7 times the square root of 7, which is the square root of 7 times 7, which is the square root of 49, which is just 7. So this is going to be 9 times 7. And this is going to be 5 at the end. Hence, we have 63 minus 5, which gives us 58. And that would be the simplification of this product here. Finally, let's simplify this one here. We got the square root of x plus 1 minus 5, and we're going to square this. That's to say we're going to take the square root of x plus 5 minus 5, and we're going to have to multiply it by itself. Common mistake is to say that you're just going to square your first term and last terms and be done with things. That's not the case. We have to multiply this by itself. And these are not conjugates of each other, so we're going to have to do this the long way. We're going to multiply our first terms together using our FOIL algorithm that we use to multiply binomials together. So we have the square root of x plus 1 times the square root of x plus 1 is the square root of x plus 1 squared. Multiplying the outer terms together, square root of x plus 1 times 5 minus 5 is going to be minus 5 of those square roots of x plus 1. Multiplying the inner terms together, we got a minus 5 times the square root of x plus 1 is another minus 5 square root of x plus 1. Finally, negative 5 times negative 5 would net us a plus 25. The square root of x plus 1 squared is just going to be x plus 1. These are like radicals. They're both square roots of x plus 1, so we can combine what's outside of them. So a -5 more of these square roots of x plus 1 is going to net us a -10 of these square root of x plus 1s, plus 25. The only other thing we can do here is combine the constant terms, 1 plus 25 to give us 26. So I'm going to call my final answer x minus 10 times the square root of x plus 1 plus 26. And that would be the end. This is as simple as it gets. This is simplified as much as possible. All right, suppose I was asked to simplify 2 times the square root of 3 plus the square root of 6, and this sits over 5 square root of 3 minus 2 square root of 6. Ladies and gentlemen, we're taught back in intermediate algebra never to leave a radical appearing in the denominator of a fraction. And we have square roots in the denominator of this fraction here. We have got to get rid of these square roots. Specifically, we have to rationalize our denominator because right now we have irrational numbers. This is an irrational number, and so is this. The only thing that's going to rationalize this denominator is by multiplying the numerator and denominator of this fraction by the conjugate of the denominator. And the conjugate of 5 square root of 3 minus 2 square root of 6 is going to be 5 square root of 3 plus 2 square root of 6. Now, the numerator is going to entail most of the work because we're going to have to take 2 square root of 3 plus square root of 6, and we're going to have to multiply it or FOIL it out, if you will, with 5 square root of 3 plus 2 square root of 6. The denominator is easy to multiply together because these are conjugates of each other. So all we have to do is square our first term, square our last term, and place a minus sign in between them. Now the numerator has to be multiplied all out, which means I'm going to use my FOIL algorithm that we use when multiplying binomials together. So 2 square root of 3 is going to have to get multiplied by 5 square root of 3. Plus, I'm going to multiply my outer terms together. That's to say 2 square root of 3 times 2 square root of 6. Plus, then I'm going to multiply my inner terms together. Square root of 6 times 5 square root of 3. Plus, then I'm going to multiply my last terms together. Square root of 6 times 2 square root of 6. My denominator is pretty easy to simplify. 5 squared is 25. And the square root of 3 squared is just 3. So this is going to be 25 times 3. 2 squared is 4 times the square root of 6 squared is just 6. That would be your denominator. Back up the numerator. 2 squared of 3 times 5 squared of 3 is going to be 2 times 5 is 10. And the square root of 3 times the square root of 3 is the square root of 9. 2 square root of 3 times 2 square root of 6. 2 times 2 gives us 4. And the square root of 3 multiplied by the square root of 6 is the square root of 3 times 6, or the square root of 18. Square root of 6, which is really understood to be like 1 square root of 6 times 5 square root of 3. 1 times 5 is 5. And the square root of 6 times the square root of 3 is square root of 18. Square root of 6, or 1 square root of 6 times 2 square root of 6. 1 times 2 is 2. Square root of 6 times the square root of 6 is the square root of 36. 25 times 3 downstairs is 75. 4 times 6 is 24. Now, 10 times the square root of 9 Square root of 9 is 3, so we're going to have 10 times 3, and 10 times 3 is 30. These are like radicals. 4 square root of 18 added to 5 square root of 18 is going to give us 4 plus 5, or 9 square root of 18. Adding like radicals together is like adding like terms together. Like if this was 4x plus 5x, we would call it 9x. But this is 4 square root of 18 plus 5 square root of 18. We call it 9 square root of 18. 2 times the square root of 36. The square root of 36 is 6. So 2 times 6 is 12. 75 minus 24 in the denominator is going to net us with 51. Back in the numerator, 30 plus 12 gives us 42. Now, the square root of 18 is not simplified. Although 18 is not a perfect square, 18 can be factored down into 9 times 2. And 9 is a perfect square. Hence, we're going to have 42 plus the square root of 9 brings us 9 out from underneath the square root as a 3. The 3 will come out here and join the 9 as a factor. All right, so 42 plus 12 here is going to be 54. And 9 times 3 is 27. So we have 54 plus 27 square root of 2 all over 51. Now, this can be reduced here a little bit. We could split this up and put the 54 over the 51 plus, and then I can put this 27 square root of 2 over 51. And if nothing else, 3 divides into both 54 and 51. 3 divides into 54 18 times, and divides into 51 17 times. So this reduces down to 18 17ths. So we have 18 17ths plus 3 divides into 27 9 times, and divides into 51 17 times. So this reduces down to 9 square root of 2 over 17. And if you want to recombine these at the end, you can. You can leave your answer like this. If you want to recombine them, since we have a common denominator, we could put this back together and call it this. And that'd be your final answer here. Or you could just leave your answer like this. But yes, it would be nice to split this up like this and reduce a little bit there. Okay. So notice we have rationalized our denominator. We got rid of our square roots in our denominator. And the only thing that enabled that to happen was by multiplying the top and bottom of this radical expression by the conjugate of the denominator. That was the key. All right, just a couple more problems to wrap up this section here. This next expression is called a complex fraction. Anytime you have fractions over fractions, you have what is called a complex fraction. And oftentimes we do run into these, and we don't like to leave them as such. We like to simplify them down to ordinary simple fractions. So we want to simplify this complex fraction here. We have fractions over fractions. To do so, the most efficient way is to determine the least common denominator of all your denominators. So the least common denominator of 6, 6x, 6, and 6x is going to be 6x. Now what I'm going to do is I'm going to multiply the top and bottom of this entire complex fraction by the least common denominator, 6x. This 6x here is going to multiply into both these fractions here. So I'm going to have x over 6 times 6x over 1 minus this fraction times 6x. Downstairs in the denominator, this 6x will distribute into both these fractions. So I'm going to have 1 6 times 6x. And I'm going to have 7 over 6x times 6x. Right here, we have x over 6 times 6x. We can cross cancel. The 6 divides into itself once, divides into 6 once, and we're left with x times x, or x squared. Here, the 6x's cross cancel or cross reduce out to ones, leaving you with minus 5x plus 14. And you need to enclose the 5x plus 14 inside parentheses because we are to minus the whole thing off, not just the 5x. In our denominator, these 6's cross reduce out to ones, and we're left with 1 times 1x, which is x. Here, these 6x's cross reduce out, leaving you with minus 7. Back in the numerator, we have x squared distributing the negative sign in here. We have x squared minus 5x minus 14, and that all sits over x minus 7. One last thing is we need to ask ourselves, can this trinomial in the numerator be factored? We need to entertain that possibility because it might lead to reduction. And sure enough, there are two factors of negative 14 that sum up to negative 5, namely negative 7 and 2. Hence, this trinomial factors in x minus 7 times x plus 2. And we can see that the x minus 7 factors now reduce out to ones, leaving you with your final answer of x plus 2. So this would be the simplification of this complex fraction. All right, we're going to try to simplify this expression here. 3 is understood to sit over 1, so is h. We need a least common denominator to simplify this complex fraction, and the least common denominator of 1, 1, and 1 plus h would be 1 plus h. Being the case, I'm going to multiply the top and bottom of this whole thing by 1 plus h. So this 1 plus h is going to get multiplied by this fraction here. And this 3 is going to get multiplied by the 1 plus h. Downstairs, we're going to have h times 1 plus h. All right, now when we multiply these fractions together, the 1 plus h's cross reduce out to ones, leaving you with 3. Here we're going to distribute the minus 3 inside the parentheses here. So minus 3 times 1 is minus 3, and minus 3 times h is minus 3h. I'm going to hold off on distributing the h into the denominator because we are going to discover something. Notice these 3's cancel out here to 0, leaving you with minus 3h over h times 1 plus h. Now notice these h's, being factors in the numerator and denominator, reduce out. H divides into itself once, h divides into this h once. We're left with our final answer of negative 3 over 1 plus h. And we're done with that. This is something that you will be doing in Calculus 1 when you look at the limit of the difference quotient as you define something called the derivative in calculus. All right, let's try to simplify this one here. We got 3 times u to the negative 1 power minus v to the negative 1 power. And that sits over 9 times u to the negative 2 power minus v to the negative 2 power. The first thing I would recommend that we do is get rid of our negative exponents. And remember, to do away with the negative sign in an exponent, we have to reciprocate the base. So 3 times u to the negative 1 power is going to be rewritten as 3 over u to the first power. V to the negative 1 power is going to be rewritten as 1 over v to the first power. This is all going to be over 9u to the negative 2 power. This all sits over 1, means the u comes downstairs, and we'll have 9 over u squared. This sits over 1, and v to the negative 2 power, we'll have the v come down into the denominator, in which case we have 1 over v squared. Now we see that we do have a complex fraction that we're trying to simplify. To do so, I would like to get a common denominator of all my denominators. And the least common denominator of u, v, u squared, and v squared is going to be u squared and v squared. I'm now going to take u squared v squared and multiply the numerator and denominator of this complex fraction by this to simplify this down to an ordinary simple fraction. U squared v squared is going to get multiplied into this fraction, in which case we'll have 3 over u times u squared v squared over 1 minus 1 over v is going to get multiplied by u squared v squared. Down in the denominator, u squared v squared gets multiplied by 9 over u squared. And then u 1 over v squared gets multiplied by u squared v squared. Now here, when we multiply these together, we can see that the u will cancel out with one of these u's here. So u divides into itself once, divides into u squared u times. And so I'm left with 3uv squared. V will cross reduce out with one of these v's up here. V divides into itself once, divides into v squared v times. And I'm left with minus 1 times u squared times v, which is to say minus u squared v. Downstairs, this u squared will reduce out with this u squared here to 1s, and we're left with 9v squared. Here, this v squared divides into itself once, divides into v squared here once, and I'm left with minus u squared. All right, so this is what I got now. The only last thing we need to entertain is the possibility of factoring these polynomials for the sake of reduction. Notice in the numerator, I can factor out a u and also a v out of both terms. And when I do that, I will leave behind 3v minus u. In the denominator, I can factor this as the difference between perfect squares. This would factor into 3v minus u times 3v plus u. Finally, we can reduce out to 3v minus u with this 3v minus u, and we're left with our final answer of uv over 3v plus u. And that is called simplified, and we're done. Okay, so this ends section R6. I think I've shown you enough of each of these problems to have success in this section. I will open up the homework on Alex for chapter R and also the chapter R quiz. Have a good weekend.